From a purely cost perspective, the most effective three-phase transformer type is star-star. Star-star transformers typically require less copper than other configurations, resulting in lower production costs. For balanced loads, there are rules that apply to star and delta connections. Star connections are used when the primary voltage is high. It reduces the voltage stress in the transformer windings and is suitable for loads that require a neutral connection. Delta connections are used when the secondary voltage is high. It provides a higher level of resistance to short-circuit currents and is preferred for loads that do not require a neutral connection. Generally, if the primary voltage is above 600 volts, a star connection on the primary side is recommended. For secondary voltages above 300 volts, a delta connection on the secondary side is preferred. For a three-phase SCR half-bridge power supply, a delta-delta transformer configuration is commonly used. This configuration provides the necessary phase shift and voltage isolation for the SCR circuit. It also allows for more efficient use of the transformer copper and minimizes the potential for harmonic distortion. When selecting a transformer, numerous factors must be considered to ensure optimal performance, safety, and cost-effectiveness. These factors include voltage levels, load characteristics, and specific application requirements. Understanding these aspects is crucial for making informed decisions that align with the intended use of the transformer. First, voltage levels play a significant role in determining the appropriate transformer configuration. Transformers are used to step up or step down voltage levels to match the requirements of different equipment and systems. The primary voltage refers to the input voltage applied to the transformer, while the secondary voltage is the output voltage provided by the transformer. The selection of a transformer must be based on the voltage levels of the source and the load to ensure compatibility and efficient operation. Secondly, load characteristics are essential considerations when choosing a transformer. The load refers to the electrical devices or equipment that the transformer will supply power to. Different types of loads have different power requirements and characteristics. For example, resistive loads, such as heating elements, draw a constant current, while inductive loads, such as motors, draw a varying current. The transformer must be capable of handling the load's power requirements, including the peak current and voltage demands. In addition, the load's power factor, which is a measure of how effectively the load uses electrical power, must be taken into account. Thirdly, specific application requirements also influence the selection of a transformer. Different applications have unique needs and constraints. For example, in industrial settings, transformers are used to power heavy machinery and equipment. These applications typically require transformers with high power ratings and robust construction to withstand harsh operating conditions. In residential settings, transformers are used to step down voltage for household appliances and lighting. These applications require transformers with lower power ratings and compact designs. Furthermore, safety considerations are paramount when selecting a transformer. Transformers generate heat during operation, and excessive heat can lead to insulation breakdown and fire hazards. Transformers must be equipped with appropriate cooling mechanisms such as oil immersion or forced air cooling to dissipate heat effectively. In addition, transformers must be protected against overloads and short circuits to prevent damage and ensure safe operation. Protection devices, such as fuses and circuit breakers, are used to interrupt the flow of current in the event of a fault. The choice of transformer configuration, such as delta or Y, also affects the transformer's performance and characteristics. Delta-connected transformers provide a stable voltage supply, while Y-connected transformers provide a neutral point that can be used for grounding. The selection of the appropriate transformer configuration depends on the specific application requirements and the characteristics of the load. Moreover, the efficiency of a transformer is an important consideration. Transformers are not perfectly efficient and lose some energy in the form of heat. The efficiency of a transformer is defined as the ratio of output power to input power. High-efficiency transformers reduce energy waste and lower operating costs. Transformer efficiency is influenced by factors such as core material, winding design, and load level. In addition to these factors, the size and weight of a transformer can also be important considerations, especially in applications where space is limited. Compact transformers are available that offer high performance in a small footprint. These transformers use advanced core materials and winding techniques to minimize size and weight. Furthermore, the environmental impact of a transformer should be considered. Transformers can contain oil or other insulating fluids that can be harmful to the environment if released. Environmentally friendly transformers are available that use biodegradable insulating fluids and reduce energy waste. These transformers help to minimize the environmental impact of electrical systems. When selecting a transformer, it is important to consult with qualified electrical engineers and transformer manufacturers to ensure that the selected transformer meets the specific application requirements and safety standards. These professionals can provide guidance on transformer selection, installation, and maintenance. Transformer selection is a complex process that requires careful consideration of numerous factors. By understanding these factors and consulting with experts, you can select a transformer that provides reliable, efficient, and safe power for your application. Transformers are essential components of electrical power systems, and their proper selection and maintenance are crucial for ensuring the reliable and efficient operation of these systems. The cost-effectiveness of a transformer is not solely determined by its initial purchase price. Factors such as energy efficiency, maintenance requirements, and lifespan also contribute to the overall cost of ownership. High-efficiency transformers, although potentially more expensive upfront, can save significant amounts of energy over their lifespan, leading to lower operating costs. Similarly, transformers with robust construction and reliable components may require less maintenance and have a longer lifespan, reducing the need for costly repairs or replacements. Therefore, a comprehensive cost analysis should be conducted to evaluate the total cost of ownership before making a transformer selection. The application of transformers at SCR, silicon-controlled rectifier, half-bridge power supplies presents unique considerations. SCR half-bridge power supplies are used to convert alternating current, AC, to direct current, DC, with control voltage and current output. Transformers in these applications must provide the necessary voltage transformation, isolation, and phase shift to ensure proper operation of the SCR circuit. The delta-delta transformer configuration is commonly used in SCR half-bridge power supplies due to its ability to provide a stable voltage supply and minimize harmonic distortion. Harmonic distortion refers to the presence of unwanted frequencies in the electrical waveform, which can negatively impact the performance of sensitive electronic equipment. Delta-delta transformers help to reduce harmonic distortion by providing a balanced three-phase voltage supply. In addition, transformers in SCR half-bridge power supplies must be capable of handling the high-frequency switching currents generated by the SCR. These switching currents can cause additional losses in the transformer, leading to increased heat generation and reduced efficiency. Therefore, transformers designed for SCR applications typically incorporate special winding techniques and core materials to minimize these losses. Furthermore, transformers in SCR half-bridge power supplies must meet stringent safety standards to protect against electrical shock and fire hazards. These standards may require the use of reinforced insulation, overcurrent protection, and other safety features. When selecting a transformer for an SCR half-bridge power supply, it is important to consult with experienced power supply designers and transformer manufacturers to ensure that the selected transformer meets the specific application requirements and safety standards. These professionals can provide guidance on transformer selection, installation, and maintenance. In summary, selecting a transformer involves a multifaceted evaluation process that considers voltage levels, load characteristics, application requirements, safety standards, cost-effectiveness, and specific needs of applications such as SCR half-bridge power supplies. By carefully considering these factors and consulting with experts, you can choose a transformer that delivers reliable, efficient, and safe power for your intended application. The efficiency of a transformer is a critical parameter that directly impacts its operating costs and environmental footprint. Transformer efficiency is defined as the ratio of output power to input power, expressed as a percentage. A higher efficiency indicates that a smaller portion of the input power is lost as heat, resulting in lower energy consumption and reduced operating costs. Transformer efficiency is influenced by several factors, including core material, winding design, load level, and operating temperature. Core material plays a significant role in transformer efficiency. High-quality core materials, such as amorphous steel, have lower hysteresis losses, which are caused by the repeated magnetization and demagnetization of the core material. Lower hysteresis losses translate to higher transformer efficiency. Winding design also affects transformer efficiency. Optimizing the winding design to minimize resistance and leakage inductance can reduce copper losses, which are caused by the flow of current through the windings. Lower copper losses result in higher transformer efficiency. Load level is another factor that influences transformer efficiency. Transformers typically operate at their highest efficiency when loaded near their rated capacity. As the load level decreases, the efficiency of the transformer tends to decrease as well. Operating temperature also affects transformer efficiency. As the operating temperature of the transformer increases, the resistance of the windings increases, leading to higher copper losses and reduced efficiency. Therefore, it is important to ensure that transformers are properly cooled to maintain optimal efficiency. There are several types of transformer losses that contribute to reduced efficiency. These losses can be broadly categorized into core losses and copper losses. Core losses, also known as iron losses, are caused by the magnetization and demagnetization of the core material. Core losses are further divided into hysteresis losses and eddy current losses. Hysteresis losses are caused by the energy required to overcome the magnetic hysteresis of the core material. Eddy current losses are caused by circulating currents induced in the core material by the changing magnetic field. Copper losses, also known as winding losses, are caused by the flow of current through the windings. Copper losses are proportional to the square of the current and the resistance of the windings. To improve transformer efficiency, manufacturers employ various techniques to minimize core and copper losses. These techniques include using high-quality core materials, optimizing winding designs, and implementing advanced cooling systems. In addition to these design improvements, proper transformer maintenance can also help to maintain high efficiency. Regular inspections, cleaning, and testing can identify and address potential problems that could lead to increased losses. The economic benefits of using high-efficiency transformers can be significant, especially in applications with high energy consumption. High-efficiency transformers reduce energy waste, lower operating costs, and decrease the environmental impact of electrical systems. The payback period for investing in high-efficiency transformers can be relatively short, depending on the energy savings and the initial cost of the transformer. Government regulations and industry standards are increasingly promoting the use of high-efficiency transformers. These regulations and standards set minimum efficiency requirements for transformers and encourage manufacturers to develop more energy-efficient products. Furthermore, financial incentives, such as tax credits and rebates, are often available to encourage the adoption of high-efficiency transformers. When selecting a transformer, it is important to consider the efficiency rating and compare the operating costs of different transformers. The efficiency rating is typically provided by the manufacturer and indicates the transformer's efficiency at various load levels. By carefully evaluating the efficiency rating and operating costs, you can select a transformer that provides the best balance of performance, cost-effectiveness, and environmental sustainability. In conclusion, transformer efficiency is a critical parameter that affects operating costs, energy consumption, and environmental impact. By understanding the factors that influence transformer efficiency and selecting high-efficiency transformers, you can significantly reduce energy waste and improve the overall sustainability of electrical systems. The configuration of transformer windings, specifically star, also known as Y, and delta connections, significantly impacts the transformer's performance and suitability for different applications. Understanding the characteristics of each configuration is essential for selecting the appropriate transformer for a given application. In a star-Y connection, the three windings are connected in a Y shape with a common neutral point. This configuration provides a neutral connection, which can be used for grounding or for supplying single-phase loads. Star-connected transformers are typically used in applications where a neutral connection is required, such as power distribution systems. The voltage between the line and neutral is lower than the line-to-line voltage in a star connection. In a delta connection, the three windings are connected in a closed loop, forming a triangle shape. This configuration does not provide a neutral connection. Delta-connected transformers are typically used in applications where a neutral connection is not required, such as motor starting and industrial power systems. The line-to-line voltage is equal to the winding voltage in a delta connection. The choice between star and delta connections depends on several factors, including the voltage levels, load requirements, and grounding considerations. Star connections are typically preferred for high-voltage applications, as they reduce the voltage stress on the winding. Delta connections are typically preferred for low-voltage applications, as they provide a higher level of resistance to short-circuit currents. When selecting a transformer, it is important to consider the grounding requirements of the system. Grounding is the process of connecting the electrical system to the earth, which provides a path for fault currents to flow back to the source. Grounding helps to protect against electrical shock and equipment damage. Star-connected transformers provide a convenient point for grounding, as the neutral point can be directly connected to the earth. Delta-connected transformers require a separate grounding transformer to provide a grounding path. The impedance of the transformer windings also affects the performance of the system. Impedance is the opposition to the flow of alternating current. Higher impedance can limit the fault current, which can help to protect against equipment damage. Star-connected transformers typically have higher impedance than delta-connected transformers. The harmonic content of the load current can also affect the performance of the transformer. Harmonics are unwanted frequencies in the electrical waveform, which can cause equipment overheating and other problems. Delta-connected transformers can help to reduce harmonic distortion by providing a circulating current path for harmonic currents. In addition to star and delta connections, there are other transformer winding configurations, such as open delta and zigzag connections. Open delta connections are used in applications where one of the three phases is not available. Zigzag connections are used to reduce harmonic distortion and improve voltage balance. The selection of the appropriate transformer winding configuration depends on the specific application requirements and the characteristics of the load. It is important to consult with qualified electrical engineers and transformer manufacturers to ensure that the selected transformer meets the specific application requirements and safety standards. In summary, the configuration of transformer windings, specifically star and delta connections, significantly impacts the transformer's performance and suitability for different applications. Understanding the characteristics of each configuration is essential for selecting the appropriate transformer for a given application. The application of transformers in electrical power systems is vast and varied, ranging from small-scale residential applications to large-scale industrial and utility applications. Transformers play a critical role in stepping up or stepping down voltage levels to match the requirements of different equipment and systems. In residential applications, transformers are used to step down the high-voltage electricity from the power grid to the lower voltage levels used by household appliances and lighting. These transformers are typically small and single-phase. In commercial buildings, transformers are used to supply power to lighting, HVAC systems, and other electrical equipment. These transformers are typically larger and three-phase. In industrial facilities, transformers are used to power heavy machinery, motors, and other industrial equipment. These transformers are often very large and may be custom designed to meet the specific requirements of the application. In utility power systems, transformers are used to step up voltage for long-distance transmission and to step down voltage for distribution to residential, commercial, and industrial customers. These transformers are typically very large and are often located in substations. Transformers are also used in specialized applications such as electric vehicles, renewable energy systems, and data centers. Electric vehicles use transformers to convert the high voltage DC power from the battery to the low voltage AC power used by the motor. Renewable energy systems, such as solar and wind power, use transformers to step up the voltage from the renewable energy source to the voltage level of the power grid. Data centers use transformers to provide reliable and high-quality power to servers and other critical equipment. The selection of the appropriate transformer for a given application depends on several factors, including the voltage levels, load requirements, and environmental conditions. It is important to consult with qualified electrical engineers and transformer manufacturers to ensure that the selected transformer meets the specific application requirements and safety standards. Transformers are essential components of electrical power systems, and their proper selection and maintenance are crucial for ensuring the reliable and efficient operation of these systems. The maintenance of transformers is crucial for ensuring their reliable and efficient operation. Regular inspections, testing, and maintenance can identify and address potential problems before they lead to equipment failure or safety hazards. Transformer maintenance typically includes the following tasks: visual inspection, oil testing, insulation resistance testing, turns ratio testing, and tap changer maintenance. Visual inspection involves checking the transformer for signs of damage such as leaks, corrosion, and overheating. Oil testing involves analyzing the transformer oil to determine its condition and identify any contaminants. Insulation resistance testing involves measuring the resistance of the transformer insulation to ensure that it is providing adequate protection against electrical breakdown. Turns ratio testing involves verifying the turns ratio of the transformer windings to ensure that the transformer is operating correctly. Tap changer maintenance involves inspecting and lubricating the tap changer mechanism to ensure that it is operating smoothly. In addition to these routine maintenance tasks, transformers may also require more extensive repairs or replacements over their lifespan. These repairs may include replacing damaged bushings, repairing oil leaks, or rewinding the transformer windings. The frequency of transformer maintenance depends on several factors, including the age of the transformer, the operating conditions, and the criticality of the application. Transformers that are operating in harsher environments or that are critical to the operation of a facility may require more frequent maintenance. It is important to follow the manufacturer's recommendations for transformer maintenance and to keep accurate records of all maintenance activities. Proper transformer maintenance can extend the lifespan of the transformer, improve its reliability, and reduce the risk of equipment failure or safety hazards. In summary, the maintenance of transformers is crucial for ensuring their reliable and efficient operation. Regular inspections, testing, and maintenance can identify and address potential problems before they lead to equipment failure or safety hazards.